So the obtained energy momentum tensor, T mu equal to rho u mu u nu plus P u mu u nu minus G mu nu. This energy momentum tensor we want to use to solve that problem that I described at the very beginning of this lecture. So we want to consider spherically symmetric ideal ball where inside it we have energy momentum tensor equal to this and outside T mu equals to 0. So the radius of the ball is at r. So we expect in such a situation, which is time independent, we expect to get static metric whose components are independent of time and it is diagonal. Static means invariant on the translations and time reversal. And we expect that this, in this situation, is spherically symmetric. So rho is a function of r only. P is a function of r only also. So it depends only on the radius. And also the metric, ansatz for the metric, we assume use the same one as it was used in the lectures 4, where we have been discussing Schwarzschild solution. So the difference is that energy momentum tensor is not 0 in Einstein equations. So the ansatz is like this, minus exponent of lambda of r dr squared minus r squared d omega squared. And this is the metric on the unit two-dimensional sphere. So these are functions of r. So this problem is absolutely static and spherically symmetric. Now, with this metric ansatz, with this metric tensor, we obtain the equations that we have already seen in the lecture 4. So the equations are as follows. We write them in a bit different manner, and in that lecture, nu and lambda were in principle functions of time. Now we consider them as time independent. So the equations we obtain are as follows. But this is just rho 0, 0, r 0, 0 minus 1/2 r. So this is just this component of the Ricci tensor and scalar. And for this metric, this is minus lambda divided by r lambda prime plus 1 r squared 1 minus lambda. So this is the first thing. 8 pi kappa p of r is equal to r11 minus half r, which is again for this metric ansatz is minus lambda divided by r nu prime 1 over r squared 1 minus exponent of lambda. And finally, let me start writing here because it's a longer equation. 8 pi kappa p of r, which is r22 minus 1/2 r, is minus exponent of nu plus lambda divided by 2 over 2 d over dr exponent of nu minus lambda over 2 minus lambda 2 over r nu prime plus exponent of minus lambda divided by 2r lambda prime. So these are the equations, the non-trivial part of Einstein equations. The rest of the equations either follow from this or trivially satisfied. Means that they just establish that 0 equals to 0, trivial relation. And probably we have to stress that nu prime as just d over dr of nu, and lambda prime is d over dr of lambda. So let me just start with the consideration of this equation. It depends only on lambda, as one can see, and can be easily solved. The solution of this equation, the solution for lambda, is, well, first of all, it can be represented like this, 1 over r squared d over dr, easy exercise, r1 minus lambda is equal to 8 pi kappa rho, which is a function of r only. As a result, the solution of this equation is that this guy is just 1 minus 2 kappa, some function of r, which I'm going to specify here in a moment. So it's like this, where m of r is the following thing. It's 4 pi integral from 0 to r dx times x squared times rho of x plus constant of integration. So, but we should have that this guy is regular everywhere. We want to have metric to be regular everywhere. Hence, this constant should be 0, constant of integration. That's the first thing. Second, we don't want to have a horizon because it's a star. So, I mean, it's not a black hole. Nowhere inside it density is such that we have a horizon. So we want to have this to be greater than 0, which imposes a relation on rho as follows from here, because r should be greater than, so 2 kappa m of r should be smaller than r. So this is a restriction on rho as follows from here. So these are the restrictions we have from the regularity. And there are more restrictions that we're going to describe now. We are looking for the solution as follows: nu of r dt squared minus lambda of r dr squared minus r squared d omega squared. And we already have found that this guy, minus lambda of r, is just 1 minus 2 kappa m of r divided by r, where m of r is 4 pi is integral from 0 to r dx times x squared rho of x. And to derive this, we have used the fact that rho is a function of r only. So, and obviously rho of r is equal to 0 for r greater than the radius of the star. And as a result, we obtain that outside of the star, this part of the metric is reduced to the Schwarzschild one. In fact, mass becomes at r, and which is a so-called total mass of the star, dr times rho r squared rho of r. But one has to have in mind that actually the total mass, real mass of the star, should be integral over the body of the star of the volume form times the three-dimensional determinant of the three-dimensional metric times rho of r. So this is a determinant of this part of the metric, and this is just volume form. So this integral is reduced to 4 pi from the angular integration times integral of rho from 0 to big R dr times r squared rho of r divided by square root 1 minus 2 kappa m of r divided by r. So this contribution comes from here, and notice that this the difference between this and this, between this formula and this formula, is due to this fact. And this m is always greater. M real minus m is always greater than 0. And this is nothing but the gravitational binding energy which sustains the star. So this is so far. Now we have to fix this quantity. To fix it, let us go on with the second equation that we have derived previously. I mean, with this equation. Minus 8 pi kappa p of r is equal to minus exponent of minus lambda r times nu prime plus 1 over r squared 1 minus exponent of minus lambda. So now we know this and this quantity from here, and we can find nu. The equation for nu is as follows, that d nu over dr is 2 kappa m of r plus 8 pi r cube kappa p divided by r and r minus 2 kappa m of r. So in non-relativistic limit, let us understand this equation. To understand this equation, let us point out that in non-relativistic limit, p is much less than rho. So here we can neglect this term in comparison with this term in non-relativistic limit. And also 2 kappa m is much, even kappa m, is much less than r. So we all, again, can neglect this term in comparison with this. As a result, the equation that we obtain is d nu over dr is nothing but 2 kappa m of r divided by r squared. And this is nothing but the Poisson equation. This is nothing non-relativistic Poisson equation, spherically symmetric version of the Poisson equation, surely, for the gravitational potential. So nu over 2 is nothing but the gravitational potential. So this, the physical meaning of this contribution is clear. It's just relativistic generalization of the gravitational potential. Remember that in the lecture describing Schwarzschild black hole, the G00 factor was playing the role of 1 plus 2v in the non-relativistic limit. So this is a similar situation here we encounter, and that helps to go further. Now, instead of the last equation, we had 3 equations. The first equation gave us the opportunity to define lambda. This is the second equation. There was a third equation. That equation was looking quite complicated. Instead of using it, we can use the continuity equation. I mean, the conservation of the energy momentum tensor. Remember that we have, in the third lecture, we have explained that GR equations of motion and this equation are not independent equations, they follow from each other. So instead of using some of the equations of Einstein equations, we can use this one. And we're going to use this opportunity. This equation is simpler. It has this form. Well, let me write it here. It has this form that 2 dp over dr is equal to minus p plus rho d nu over dr. So this equation follows from this one. And if we use this in here, we obtain the following equation for the pressure. It has the following form: dp over dr is equal to minus p plus rho times kappa m of r plus 4 pi r cube times kappa rho of r divided by r times r minus 2 kappa m of r. This is so-called Tolman, this equation is so-called Tolman-Oppenheimer-Volkoff equation, which describes hydrodynamic equilibrium for the star, for the hydrodynamic equilibrium of the star. We are now going to describe the solutions of these equations and specify the equation of state for the liquid. To go further, we need to do that.